All right, we're going to go ahead and get started. So I don't want to take up too much time from our speakers. You are in Seamless AI Systems 1. There's a follow-on session this afternoon. Welcome to our speakers and welcome to our audience members. Thank you so much for joining us from whatever time zone you're in. You're at 9:30 Mountain Time right now. And hopefully next year we're going to try and do this for sure in Boulder so you can see the beautiful mountains that we're passionate about here. All right, so you're looking at my screen in brief here. Welcome, thank you again for coming. We have 5 awesome talks. We have 2 highlights. We're going to bookend the session with a highlight at the beginning and a highlight at the end. We have a talk by Shannon Rankin, Daniel Woodrich, Thomas Vandal, Matt Brown, Damien Sileo. And if basically we have roughly 18 minutes per highlight talk and 11 minutes per regular talk. And we need to build the questions into that time. So speakers try to end a little bit earlier than that if you want to have questions in real time. If we have time at the end, we'll use it for a conversation around questions to everybody. And then I want to announce, and Brian Meyer is here to do 2 things: help us keep on track, and also post in the chat where you can start to post your questions in the Slack channel. So the Slack channel is as 07 Seamless AI System. You can see it on the right-hand side of the screen. So why don't we go ahead and get started with the first speaker, Shannon Rankin. If you're here, please go ahead and share your screen, and I will stop sharing mine to ease that. And this is a highlighted talk combining the power of citizen science and artificial intelligence to make new discoveries in our ocean soundscapes. Could everybody else stop their video for our speaker? Thank you. And Shannon, take it away.
Hi, so assuming you all can see my talk, please let me know if anything's wrong.
It looks good.
Okay, great. My name's Shannon Rankin and I work at Southwest Fisheries Science Center. I'd like to introduce a project that we call Sound Discoveries, which combines the power of citizen science and artificial intelligence to make new discoveries in our ocean soundscapes. Sound Discoveries is a bit of a vision. It's an idea of how we can use new technologies to revolutionize the way we work with our soundscape data. So while this vision is focused on acoustic data, which is unique in a lot of ways, many of the processes can be applied towards other data types. So like any good vision, we need a good team and good resources. And at this point, we've assembled a visionary team who I'll introduce to you shortly. And then the next step is to identify resources to turn this vision into a reality. So our science is called Passive Acoustic Monitoring. We listen to the ocean, and the ocean has a lot to say. Sound travels exceptionally well in the ocean, and animals have evolved to take advantage of this feature. So our main focus has been on whales and dolphins, but there's also great potential to study fish and invertebrates as well. We can also detect geological sounds such as earthquakes, physical sounds such as rain, and of course, anthropogenic or man-made sounds such as ship noise. So our massive acoustic archives can also be used to address new questions. In addition to studying our biological resources, our data can help us better understand human use of the ocean, impacts of noise on animals, and the soundscape can be used as an indicator of habitat health. Unfortunately, as we collect tens or even hundreds of terabytes of data every year, we're increasingly relying on automated processing, and over time, we're losing touch with our data. We're losing our ability to actually explore our data. So we are wondering, how can we use new technology to facilitate exploration of this data to address these emerging issues? And that's the fundamental question that led to the vision of Sound Discoveries. But first, I'll explain how we currently make discoveries. So how do we do our job? The first step typically involves recording sounds in the presence of a whale or dolphin or whatever it is. Once we know their calls, we can then build automated systems to detect and classify these calls. And then we can apply these automated systems to our big data, which can then teach us about their distribution or their migration patterns. And a good example of this is Longman's beaked whale. So when I started, we knew almost nothing about this whale, although we might encounter them once during a long offshore survey. And eventually we had enough information to identify characteristics of their calls that differentiated them from other species. Then we could run automated methods to find these sounds in our big data, classify these sounds as longman beaked whales based on these characteristics. And then eventually we can use this archive to better understand the species. So this is the typical approach. Start with a recording from a known species, develop automated methods, and then apply those methods to our big data to ask big questions. But sometimes we discover the sound first. We might record a sound from some unknown sound source, then build our automated methods, detection and classification, and apply those to the big data to learn about the distribution of the sound. And then hope that in some point in the future, we can learn who is actually making that sound. And then once we do learn the identity of that sound, we have this instant knowledge about the sound source itself. A great example of this is the mysterious boing sound in the North Pacific. Early Navy sonar men listening for enemy submarines detected this sound throughout the North Pacific Ocean. And the plots on the right are from an old unpublished Navy report. And they found that there was a peak of boing detection near Hawaii in February. So it was likely due to an animal that was migrating south in the winter. So here we have a case of a large body of knowledge about the distribution of some unknown sound in the North Pacific Ocean. Likely a migrating animal, but essentially still a mystery. And then in 2002, we were on a survey off Hawaii and we heard the boing. And then we could track it using acoustics until we ended up with a minke whale breaching right off the bow of our boat. So the crazy thing is the minke whale wasn't even on our list of species for this area. We didn't even think they went to Hawaii. And that the single match between a known sound and the minke whale forever changed our understanding of their distribution and migration patterns. And so we've also had cases as recently as this year where we used the understanding of a distribution of a sound to lead an expedition that ultimately may have discovered an entirely new whale species. So I can't emphasize enough how important these discoveries really are. And there are unknown numbers of undiscovered nuggets in our existing archives. And this brings us to our big data challenge. We now have more ways to collect data. Our data is of higher resolution, our recordings are longer, and all of this adds up to an exponential increase in our NOAA archive. We've only studied a small fraction of the petabytes of data that we have, and we simply cannot explore the data the way we used to. So we need a new approach to discover sounds, one that uses new technology to accelerate the rate of discovery, one that can easily lead to development of new AI models, which then can easily be applied to our archive data. And we need this new technology to basically decrease the latency in developing data products that are critical to inform management of the expanding blue economy. And really importantly, for this to be successful for NOAA's needs, this approach must work directly with our existing archive data. It needs to be highly automated, open source, and easily adopted across NOAA. And so this is where Sound Discoveries comes in. Sound Discoveries is a vision to combine new technological advances in cloud computing, machine learning, and citizen science to fundamentally shift the way we work with our data. And critical to Sound Discoveries is this seamless connectivity between each of these platforms to allow for iterative learning between machine learning platforms and both the citizen and expert scientists. And we're not starting from ground zero. We're working with partners who have a long history of development on their respective platforms. So Carrie Wall has been developing the Passive Acoustic Archive, including a partnership with Google to provide access via the Google Cloud platform. Anthony Hoogs and Matt Dawkins have been developing Viame, which is a really incredible platform for creating AI models for detection and classification from images and videos. And then Laura Truey at Zooniverse, and Zooniverse is arguably the leader in online citizen science platforms. So our Discoveries visions includes modifications of each of these platforms to better accommodate passive acoustic data, as well as the connections between these platforms that are critical for its success. So I want to give you a few examples of how we imagine this working. So first, we'll look at sound discoveries from the perspective of our NOAA researcher, Anne Simonis. So Anne currently uses specialized acoustic software for analysis, and she could import those annotations into Viame, or she can work directly within Viame. Those labeled annotations can then go into developing AI models in Viame and then be applied to our archived data set at NCAI. And she can also share those models with colleagues. But Anne also interacts with the Zooniverse platform. This seamless transfer of information between NCAI, Viame, and Zooniverse allow her to easily prepare specific projects, say as validating seal bomb detections. But she can also monitor the exploratory Zooniverse project, which we affectionately call the Sound Disco. And this is where citizen science lead their own exploration of our data. So this seamless interaction between the technologies allows Anne to focus her limited time on actually applying data to meet our management needs and to interact with citizen scientists. So these are human tasks, not computer tasks. And these are the tasks with the greatest satisfaction. So the idea is better results, less pain, more joy. So the Sound Disco also gives citizen scientists the opportunity to participate in our research, to lead their own projects, or to contribute to new discoveries. And here I'll imagine how it might look like from the perspective of a student at Mount Edgecombe High School in Alaska. So Mr. Mahoney here in the ball cap teaches a biology class with researchers at Scripps Institution of Oceanography. This program called CTEC allows students to work with acoustic data to do authentic research. And while there's great interest in applying the CTEC model to other schools, the software is just too complicated. And Mr. Mahoney's been doing this for a long time, so this works for his classroom, but it's just not scalable. But Zooniverse develops their platform with the user in mind. So with a Sound Disco, students spend minimal time learning how to use the platform, and more time is focused on actually doing science and research. So as an example, let's take Aiden, who's standing here next to Mr. Mahoney. In class, Aiden might be exploring data in the Sound Disco. Now, Anne likely processed this data for known sounds, but these recordings have not yet been explored by ears and eyes. As Aiden scans the data, he finds these curious sounds that are similar to the old school video game Pac-Man. And it doesn't match any of the sounds in the tutorial, and those sounds are unfamiliar to Mr. Mahoney. So say Aiden annotates dozens of these calls in an hour time period and labels them as unidentified. Now, as part of the normal sound discoveries, those labels will go into Viame for future consideration. But, like any curious person, Aiden keeps thinking about these sounds. Are there more of them out there? Are they from an animal, something man-made? One of the great things about Zooniverse is the ability for citizen scientists to reach out to researchers with questions. So Aiden can make a post on Zooniverse Talk to ask about the calls he found. And then Anne, who's monitoring that feed, reads Aiden's post and recalls that, someone on her team, Shannon, had mentioned hearing a strange Pac-Man sound off Peru once, but never hearing it again. So then Anne can readily find Aiden's annotations in Viame, create an AI classifier to look for more of those calls in the archive data. And maybe we'll get lucky and find other matches to this mystery sound I heard off Peru a long time ago. And so this is the magic of sound discoveries. the Sound Disco creates a space for both citizen scientists and NOAA researchers to work together with acoustic data and make new discoveries. It's a win for NOAA in that it allows for efficient analysis and a new model of discovery. And it's also a win for other researchers as VIAME allows us to readily share these discoveries. But it's also a win for citizen scientists in that they can readily engage in authentic research. So when I tell people what I do for a living, that I study whale sounds, common response is, oh, I wanted to be a marine biologist, or people have some dreamy vision of sitting on a sailboat listening to humpback whales sing. And that vision, to be honest, is what got me started down this road. And our team strongly believes in the power of acoustics to encourage a love of science. But the truth is, acoustics is hard. Our data is enormous and software programs are really complicated. But sound discoveries can change this. Our science is naturally interdisciplinary, so this dreamy vision of listening to humpback whales sing can be applied towards studies in biology, physics, math, computer science. So why not take the advantage of this allure of whale song to inspire future scientists? So we have a team of teachers that we're going to work with to help ensure that we have a human-centered design of the Sound Disco so that it's easy to use. We're going to make sure that it's scalable and open source so that it's available to educators and scientists or individuals with few resources. And ultimately, this will help improve the equity in science and science education. So where are we now? This started with a vision, and then we needed to identify the right team to turn this vision into a reality. And we're currently on the lookout for resources so that we can put our plan into action. And the real tricky thing here is that for this to really serve NOAA's needs, we need this to be built in a manner that focuses as much on the interconnections and the access to NOAA archives as to the development of each of the platforms themselves. So NOAA is notoriously understaffed. I'm the only Fed on our team. And so while I know that Sound Discoveries has the potential to revolutionize the way we work with NOAA data, it must be developed specifically with NOAA in mind, and it must have a very low barrier of entry for NOAA researchers.
2 minutes.
But if it's developed in the right way, the Sound Disco will allow each one of us to experience that joy of listening to humpbacks singing or the thrill of making new discoveries. So anyway, we do have an amazing team, and I want to thank them. Their combined vision and experience is really inspirational, and I hope you can find something about this idea in your research as well. So I think I have a minute for questions.
Hi, Shannon. Yes, I'll pull one out of, so everybody, there's the link to the Slack channel. So post your questions there and the conversation can go on. Here's one for Shannon from George Cutter. Are the acoustic data spectrograms converted to 3-channel image format for analysis in VIAME?
Yeah, we've actually had a discussion on this, and we haven't started this research. We've only started the discussion and creation of the vision. And so we think it'll be done in stages, starting off with what are called long-term spectral averages, but we need the ability to zoom in and zoom out, and in both time and frequency. And so we'll probably start with only the visual component of it, which would be linked to the audio. And then eventually we would lead to a more truly integrated fashion, but we would incrementally get to that point.
Awesome. Thank you so much, Shannon. Amazing talk. Let's transition to our next speaker, Daniel Woodrich. And the title is Instinct and the Dream of an End-to-End and Beyond Data Pipeline for AI Programs in Passive Acoustic Monitoring. 11 minutes, including questions, if you could, Daniel.
Great. Thank you, Rob. Hi, everyone. My name is Dan Woodrich. I work with the Alaska Fisheries Center Marine Mammal Lab Acoustics Group. I'm the lead architect, developer, and end user of Instinct. Today, I'll be presenting on Instinct and the dream of an end-to-end and beyond data pipeline for AI programs and passive acoustic monitoring. Environmental acoustic data are collected by fisheries science centers to monitor cetacean and pinniped species. As we learned in the last talk, this is called passive acoustic monitoring. The large quantities of generated data make manual analysis of these species very time intensive. AI and machine learning tools have become increasingly effective, popular, and accepted in PAM to help bolster monitoring efforts and address the big data challenge. As our use of AI grew in our lab, we needed a way to consolidate our workflows. Data pipelines atomize data processing steps in a workflow, which controls complexity by reducing large workflows into their component parts. Instinct is an in-house designed workflow system that uses data pipelines to manage the complexity associated with expansion of AI projects. It is free, open source, and available on Linux and Windows. Damien is an AI application that also uses data pipelines, but is currently not featured for end-to-end acoustic workflows. Getting into why Instinct exists. Instinct's primary purpose is to raise the floor for AI in passive acoustic monitoring. Instinct makes powerful AI workflows easily accessible to the PAM community. For those that are looking to initiate their AI programs with a low buy-in, Instinct is a great tool to get off the ground quickly using the hardware you already have. Instinct shines as a tool for data scientists. The pipeline is implemented in Python, and lower-level data processing is language agnostic. The hierarchy of Instinct pipelines allows for customization at several levels. Instinct's architecture helps encourage design of more general, reusable data processing steps. And finally, the design of Instinct keeps the software light and flexible. The software is interfaced through the command line, parameters files, and customizable pipeline components. Here are some examples of the syntax to execute an Instinct job in the command line and example outputs you get for success as well as for failure. But what exactly is Instinct? Instinct is built on top of Luigi, which is a Python module for building data pipelines. Instinct has 4 levels of hierarchy: jobs, pipelines, processes, and methods. We'll talk first about the pipeline architecture, which is dictated by pipelines and processes. Pipelines define the flow of data through a sequence of components. Processes are a pipeline component with consistent inputs, outputs, and a data processing step. Important principles to note are that 1, pipelines and processes are interchangeable within pipelines, and therefore pipelines can be nested. Here's an example pipeline here on the right composed of 3 processes. We will use this pipeline to demonstrate modularity. This pipeline gets us metadata, ground truth data, and converts these outputs to a Raven Pro format for viewing. Now, without changing the function of the pipeline, I can swap in another pipeline to replace the second process. The original pipeline still performs the same objective, but the time frequency box data source has been swapped. So before it was ground truth, and now it is detector outputs. Note that the second pipeline additionally has nesting. This pattern allows for reuse of pipelines, which helps limit redundancy between similar workflows, and is another way that you keep the code in check. Methods are internal to processes. They dictate the way that the process is performed, and generally perform the heavy lifting of the actual data processing. They're called by a system subprocess, which kind of breaks the thread and allows you to dump memory for those that work in languages like R. They can be implemented in the language of choice. Currently, we have methods written in R, Python, and compiled MATLAB. Methods can also input parameters to control their function. I'll show an example of how methods can be used in a pipeline. For an event detector process, which will arbitrarily make this one, an example of an internal method could be a spectrogram correlation or an energy detector. Both methods, although different approaches, have the same inputs, outputs, and objective, so they are defined as interchangeable methods within the process. In addition to the customization possible, we have designed basic features that are available out of the box to implement a variety of acoustic workflows. These include metadata standards for inputs, pipeline intermediates, and outputs, retrieval of sound files and flexible folder organization, which prevents having to copy actual data files, which gets very unwieldy, rapid on-demand acoustic data decimation, Raven Pro integration, routines for querying and annotation, automated model performance evaluation, including statistics and visualizations, and importantly, a versatile base detection algorithm, which allows for rapid development, training, and deployment of AI detectors. The underlying design is a combination of a signal-specific event detector and a random forest classifier. Ground truth data annotated for only positive instances of the desired signal are used to automatically label results of the event detector on the original ground truth data and train the classifier. The two-stage design is particularly adept at high precision applications, for instance, discovery of rare signals in large data, or robust detection of a high calling rate species. The following case studies demonstrate the flexibility and utility of instinct features in a variety of our common AI workflows. In the interest of time, I'll go quickly through these, but they can be viewed further when the conference materials are made available. For our first study, the instinct base algorithm was applied to 2 fin whale call types to monitor the occurrence of the species in our dataset. Using a limited training set, we ran the algorithm on over 250 year-long mooring deployments, which allowed us to uncover previously unknown spatiotemporal trends of fin whales in our data. This analysis demonstrates Instinct's capability for big data processing and how it can generate robust presence information on a high calling rate species such as fin whales. The new data produced from this analysis can be used in future model training to further strengthen the model and increase our knowledge and confidence of when fin whale occurrence trends in our system. While fin whale detection is, of course, not a new capability to science, this example shows how Instinct was able to raise the floor for our lab and use AI to address a need in our conventional monitoring. For our next case study, the low moan is a rare, novel call type we opportunistically discovered in the field. Using limited training we found in our archival data from a single seasonal peak, we were able to create a detector for the call with the Instinct base algorithm to further explore its occurrence in our data. The results of this employment uncovered a spatiotemporal trend and gave us many more instances of high call presence to draw from, to both further characterize the call and further refine and train the model. The third case study is our creation of right whale call type detectors with Bering Sea training data applied to data from the Canadian Department of Fisheries and Oceans collected off of British Columbia. The detector performance of the models trained on the Bering Sea data can be viewed below for both the upcall on the left and the gunshot call types. This visualization is a precision recall curve, and it's offered as a convenient built-in feature for Instinct. Like the last example, these detectors were used for discovery, but in this case, on data previously unanalyzed for the presence of the critically endangered North Pacific right whale. After applying detectors and verifying outputs on 25-year-long mooring deployments, we were able to successfully identify acoustic presence of the right whale in these waters. Establishing true presence was a critical result. First, for its potential impact for understanding of North Pacific right whale presence in the region, and second, as it will allow for performance assessment and retraining of these models, which were initially applied cross-region in a very experimental deployment. Finally, this case study shows the modularity of Instinct outside the base algorithm. Here, we integrated an externally produced deep learning model from the Pacific Islands and Google collaboration to detect humpback whales in their data. We ran and tested this model under different conditions with built-in Instinct performance evaluation. The curve on the left is the model tested using only binned humpback data as a positive result, while the right is the model tested using other low-frequency calling species, including bowhead and right whales, as a positive result. The ability to integrate and assess detection models from other labs represents powerful potential for methods sharing for Instinct users and may help promote more multi-regional model training efforts in the future. So end-to-end detection workflows are on their own difficult to achieve, but it is also only a part of the battle for your AI program, as the need for integration with standalone databases will become prominent. A standalone database will allow you to leverage outputs as inputs in successive rounds of training for superior model performance. Coming goals of Instinct are to integrate more strongly with metadata databases to move from end-to-end to a more full circle lifecycle for our models. Tethys, as well as data warehouse platforms such as Google BigQuery, are under further consideration for this purpose. So what's next for Instinct? First, we hope to begin collaboration with other fisheries science centers, research institutions, or any interested project contributors to make Instinct more general to community data standards.
2 minutes.
We are happy to collaborate with developers of other platforms in pursuit of best practice in AI workflows. Our main goal is on the challenge of end-to-end detection workflows for those in the PAM community. So we support and we're eager to become contributors for development of best practice solutions, whether that's Instinct or something else. We hope to continue our development and use of the system to both in-region and out-of-region applications. I'd like to thank the following persons and agencies for supporting Instinct and its applications, as well as the data collection and analysis that our AI program is built upon. So here are two technical memorandums for further reading on Instinct, as well as a link to the project GitHub. Want to thank you for your time and thank the organizers. Please feel free to contact me with any further inquiries offline, and I'll now take any questions if we have one.
Great talk, Daniel. Very exciting. Yes, so looking in the Slack, I'll just pick, we've got a question from Scott Beers and also one from George Cutter. I think we've got time for at least the first one really quickly. Has an Instinct pipeline been implemented using real-time data, like from a cabled observatory? If so, can you point us to case studies? If not, do you think it would be feasible? Just a few seconds on that.
Currently, we mainly use it for archival. We did containerize it at one point for an experimental cloud deployment. So if the real-time system can run a container, then I think it's not, it could be used for that. However, not out of, it hasn't been designed for that out of the box. But if you are interested in setting up with our pre-trained models on any of the signal detectors, or if you even have ground truth, I'd be happy to talk more about potential for being able to set up something like that. Out of the box, though, it's mostly been used for archival data as of right now. Thanks for the question.
Okay, thank you, Daniel. And you've got another question from George Cutter in the Slack. I'll let you handle it there. And if you think of any other things, the conversation can continue. So thank you for your talk. Let's go and transition now to the third speaker, Thomas Vandal. If you could show your screen. Your talk is titled GeoNEX-ML, a machine learning system for geostationary satellite imagery.
Screen. Cool. Can everybody see? Can you see?
Yes, looks great.
Awesome. Thank you, everybody. So welcome. I am Thomas Vandal. I work at the NASA Earth Exchange at Ames Research Center in Silicon Valley. At the NASA Earth Exchange, we host most of the Earth science data on our high performance computing systems that NASA outputs, and we do processing and collaborate with a lot of scientists on different sorts of problems. So today I'm going to talk about some of those problems as part of our geostationary project. And this title, GeoNEX-ML, a machine learning system for geostationary satellite imagery, in collaboration with my colleagues at NASA and also at the Goddard Space Flight Center at GMAO in Northeastern. So NASA they have about 20 plus sensors that are flying satellites, and they're collecting data with all different sorts of sensors, resolution, spectral, temporal, and spatial, for all different sorts of applications. And this data is expected to grow exponentially into the future with more and more sensors going up. And then along with also model outputs that we generate and intermediate data sets, really make this data very large, heterogeneous, and quite difficult to work with. And transferring models across sensors is proving to be a challenge and is requiring significant human effort. So a lot of this work I'm going to talk about is trying to build efficient machine learning pipelines that allow us to work with low-level satellite data mostly at level 1, level 1B, where the data is lightly processed, but it gives us kind of some raw outputs to work with and build a good foundation on how we want to build the machine learning directly from the observations rather than required a lot of intermediate data sets coming in through models. So at GeoNEX-ML, we have provided a top of atmosphere from the NOAA L1B, which we process into a geo-corrected, solar-corrected product. And we put this on a grid such that we can compare with MODIS and other sensors quite well. And the point of doing this is for us to get some data over the land, so land surface information, diurnal cycles, such that we might do with MODIS. Because given these new geostationary satellites, we have this really high temporal frequency. We have 16 spectral bands and 500 meters to 2 kilometers spatial coverage, almost globally. And there is a bunch of different geostationary sensors around the globe. And we're looking to put all of those geostationary sensors together and be able to do global monitoring in near real time. So some of the processing challenges that we've had, data storage, computationally expensive. And one of the big challenges is when we develop a model for Himawari spectra, it might not be normally not applicable to GO16 spectra. So all the lookup tables and everything need to be updated. And this is a very time-consuming process. So I'm going to discuss 5 applications of AI that we've developed in-house. One for virtual ascension and spectral synthesis, another for temporal interpolation between geostationary images. The next 2 will kind of look at physical model emulation and emulating low Earth orbit models. And the last one, atmospheric motion with optical flow. So this example, we are interested in combining all of the geostationary sensors that we have available into an individual product that kind of joins them all together, has them on the same spectra. However, like in this example, Himawari has a green band, and GO16 and GO17 do not have a green band. In contrast, GO16 has a Ceres band and Himawari does not. So what we did here is we built this unsupervised translation model that allows us to translate from one sensor to the other and kind of generate spectra that might have been unobserved. And given that this model trains in an unobserved manner, we do not need overlapping observations, which can be pretty difficult to generate those training data sets for. So this is an example of the level 1 processing, which allows us to get everything in the same domain and then allow us to run any models that were applicable on any of the sensors. We can translate to that sensor and then apply the model on that. The second level 1 processing step that we're interested in is seeing if we can interpolate intermediate frames in the 10-minute full disk observations. So with the geostationary, we have both full disk, CONUS, and mesoscale observations. Mesoscale, they basically point the sensor at an interesting event, weather event that's happening, and we can capture 1-minute observations there. And this is obviously motivated by extreme events and having to monitor things like convection. So, however, we do not get any of that information, say in South America. We very rarely would point it down there. And we might want to have 1-minute data over the whole full disk to actually analyze these convective events. So we applied this optical flow super slow-mo interpolation approach, which allowed us to do a kind of a time-dependent interpolation. And this work was recently published in IEEE and NLS, which will be coming out in a special issue soon. A level 2 processing step that we want to be able to apply to the raw spectra is atmospheric correction for surface reflectance. Surface reflectance allows us to analyze and monitor surface conditions such as vegetation for agriculture, burned area, and so forth. So we had a model that was developed for Himawari 8, and this was the IAC model for atmospheric correction. Generating the lookup table for that was quite complicated, and transferring that lookup table to a new set of spectra that are just slightly different on GO16 has been a very challenging task. So our goal here was to see if we could emulate the Himawari model that we developed And then we could apply it to Go16 using our level 1 processing step. And this shows examples of us doing the emulation on the Himawari Mayak, along with the cloud mask and uncertainty estimation that we get from Bayesian deep learning and our internal kind of classifier that we're doing. And we can see, just looking at it quickly, that the Mayak cloud mask, this can be easily seen on the lowest row here. We got these blocky areas and so forth, and this is due to various processing steps that happen within Mayak. Our approach is a little bit cleaner. We're able to kind of understand a little bit better what's under these light clouds and filter a little bit more effectively, while also having this uncertainty information. So we're aware of where our predictions might be off. And this is an important part for interpretability. A second example of a level 2 processing step. So this was presented yesterday, this work by Kate Duffy. And what we're interested to do here is see if we can learn a mapping from geostationary to land surface temperature from the MODIS sensor. So the MODIS land surface temperature is well calibrated. It's been developed for years. And building, kind of porting these sensors, I was porting these models over to Go16, Go17 is non-trivial. And NOAA has some products out for LST at lower resolutions, both spatially and temporally. So we want to be able to apply this almost in real time on the 10-minute data and run that emulation. And we're finding that similarly as the atmospheric correction, the cloud mask works quite well, and surprisingly kind of consistent time series that we do get from this data.
2 minutes.
2 minutes, great. And then the last application I'm going to talk about is dense optical flow for atmospheric motion vectors. So atmospheric motion vectors are one of the most important variables that go into numerical weather prediction. It initializes the direction and so forth of the numerical weather model. This is used within data assimilation also, and to model wildfire plumes and nowcasting. So we're interested in seeing if we can apply optical flow to kind of sequences of images to actually capture these flow vectors. This example that I show here is on Hurricane Ida. Oh, I spelled that wrong on the thing. We can see that the cyclone has the counterclockwise spin that we would expect. And there's also the kind of clockwise outer ring of the storm that we're capturing. So these sort of patterns are not quite observable from the current atmospheric motion vector approaches. So quickly going through some challenges and lessons learned. Accurate training examples is always a top priority. For most of our work, I don't consider the machine learning and computer vision problem as being a huge issue. There's also, we have the interpretability problems and so forth in it, but actually generating accurate training examples is the most important part, and really understanding and normalizing the data correctly is much needed. The last thing I'll point out is the one difficult thing that we found for training the machine learning models has been optical flow. That's been pretty complicated, and we've been learning those on numerical simulations and then applying them onto Go16 and 17. And future work that we're interested in is we want to move this data processing on cloud services, add more sensors to our GeoLeo modeling, cascading uncertainties between levels. I'm personally very interested in generative modeling that we were doing for the spectral synthesis work. And these are some links and some information that you guys can contact me. Most of the code for at least the first 3 applications are all open source, so you can go download them. And yeah, there's some other work on GitHub on super resolution and so forth that might be of interest.
Thank you so much, Thomas. I have to break in, but it looks like you're probably on your last slide. Is that correct?
Yep, this is it.
Awesome. All right. I posed a question to you in Slack. Others, please check out the Slack channel. I'll post some nice questions for Thomas. And thank you for your talk. It was really interesting. Let's go ahead and transition to our next speaker, Matt Brown, on Adapt Drone Payload for Data Collection and Real-Time AI Processing in the Field.
Thank you, Rob.
Yeah, I can see your first slide and you, so take it away.
Okay, great. As Rob mentioned, my name is Matt Brown and I'm from Kitware. I'm excited to present some of our recent work on a NOAA-funded collaboration between Kitware and the Aquasi group from the University of Alaska Fairbanks to develop a general purpose drone payload to support data collection and real-time processing for beyond line of sight applications. We call this the ADAPT multi-mission payload because our long-term goal here is to develop this into an open source foundation for general purpose applications for a wide variety of missions, a number of which you can see here on the slide. But there's two main threads of utility provided by this payload. One is for actual raw data collection. Typically, this would be image collection. The system provides optimized routines, real-time quality control, and feedback, even in cases where the drone is well beyond line of sight, so that you can really guarantee that you're collecting good data when you're on these field missions. The other thread is supporting operations where having insights from the data that you're collecting arrive with very low latency. For example, some of these applications for disaster relief, where you would want to know how the environment is evolving with very low latency. So we're actually deploying state-of-the-art deep neural network computer vision, whether that be semantic segmentation or object detection, on board the payload. The analytics are geo-registered and wirelessly downlinked over a low bandwidth connection to a ground station and then beyond. And I'll say that if you think this system is something you or your organization might be interested in, I'd encourage you to check out our website here on the bottom. And I'll also send the link right here in the Slack chat so anybody can check that out. So the development for the ADAPT payload is supported by a NOAA Phase 2 grant, which we're about halfway through our 2-year schedule. And on this effort, we've focused on one specific mission, monitoring the condition of frozen rivers to possibly be able to better predict catastrophic flooding events that occur due to ice jams. So here we can see an image and some statistics from the 2013 Galena flood, which was due to an ice jam on the Yukon River, which caused extensive damage both in dollars and disruption of livelihood. So we took inspiration from NOAA-funded work by our collaborator, Aquasi, from 2017, and they were investigating the effectiveness of drone surveys of ice conditions on the Circle River in Alaska. And that work showed that drones can be very effective in collecting the data to study and possibly predict river outcomes, but it made a number of bottlenecks very clear in the data exfiltration and data dissemination processes. So the question we asked is whether real-time deep neural network computer vision could actually be applied on board the UAV on a small low swap computer so that we could actually distill down the critical essence of the river state. And then those summary analytics can actually be transmitted wirelessly to a ground station somewhat nearby. And then due to the smaller compressed data volume of those analytics, passed on further to the decision makers. And we envision the ADAPT payload supporting somewhat of an iterative workflow, as you can see here on this slide. The payload itself helps you collect better data through quality control and better curation of that data and the supporting metadata. And then you would take it home and you would integrate it with something like the DIY deep learning system, Viame, which you heard about a little bit earlier. And a colleague of mine is also going to be talking at 1:45, Matt Dawkins, on enhancements to Viame. But the idea is you bring this data into Viame, you start to train a model that extracts the insights from that ice imagery, you upload it, it helps you collect better data going forward, and you iterate this, and then over time your ice analysis models get better and better. So specifically, we're interested in whether semantic segmentation of the imagery can be used to distill out these critical features, encoding the overall river ice state, because you can really compress those analytics very well. So here in this image here, you can see these are results from the end of our phase 1, where we trained and tested on subsets of that circle river ice data collection. So you can see as this scans across, those are the dense outputs automatically from our segmentation system. And then you can distill these down into polygons. All of this ran on a small NVIDIA Xavier computer, which was kind of what we were trying to prove out on the phase 1. Is this even possible from a data throughput standpoint and a utility of the analytics standpoint? So as I mentioned earlier, a goal for the ADAPT payload is to be something that a variety of research groups and organizations can use as a foundation for similar work. So we've made all of the documentation, the COTS parts lists, CAD models, all of the software, all publicly available with open source licenses. The total build cost is in the range of $6,500 to $8,000 for this payload itself, additional for the actual UAV. And again, if you're interested in this system, I'd encourage you to check out the webpage. So here we can see a fully assembled payload with all of the major components highlighted. The camera is adjustable between nadir and forward-looking continuously. The GPS INS provides geolocated pose for the payload as imagery is collected. Carbon fiber shell is very durable. We actually found that out in the field. We had a minor mishap hitting a tree, and the payload was completely fine, as well as the Wi-Fi downlink here shown at the back. So here we can see the system mounted on our UAV. These images here were actually taken last week, hot off the press. We were in Fairbanks, Alaska, doing our first major field test here along the Tanana and Chena rivers. So this initial round of flight testing was really focused on demonstrating the functionality of the data collection capabilities of the system and proving that we can run a deep neural network segmentation network in real time and actually get those results in real time back to a ground station for quality control and analysis. The model that we actually ran here was earlier phase 1 model that we trained actually on air sim data. So the focus here is not necessarily on the quality of the segmentation results. It's more on the fact that it actually does run in real time. The network that we're training at the moment for ice segmentation work is identical in size. So the fact that this model runs is a testament that this future model will be fully capable. What you're seeing here is the live feedback. This is actually a screen grab live from the laptop that we were running to monitor the system. Right now, the system is about 2,500 feet away from our base station where we were situated. And you can see the imagery at the top here is a reduced resolution view. It is shrunk down on the payload itself so that we can send it out over the low bandwidth connection. And you get live histograms to maintain good exposures. And here we can see the segmentation results along with all of the analytics that are useful. And similarly, here we can see this was 2,700 feet away where we could actually interrogate focus remotely, which is a very, very useful thing to do. And for these, the ultimate goal is to support beyond line of sight operations. Nothing about the system precluded us from flying beyond line of sight other than we just didn't get permission for these particular flights. So we pushed it to the bare edge of line of sight here. You can see an inset view where the UAV is a tiny kind of smudge in the distance. And with briefly with the remaining time, I'll highlight one of the successes and one of the things we paid a lot of attention to with this system was the temporal synchronization between the imagery and the INS data. Anybody from the SLAM community can attest to how critical it is to actually get those streams synchronized to milliseconds or better. If you want to start exploiting some of the visio-inertial properties of the pair and do things like visual localization of the payload, as well as mapping of the environment in a much more efficient way than just vision alone can provide to you. And I won't go into the details of these curves, but they were an offline strong verification that things are very well synchronized, and we have a very rigorous routine for maintaining synchronization. And very briefly as well, I'll talk a little bit about the benefits of adding geospatial awareness and good geospatial awareness to the data collections. These are very large mosaics of imagery that we collected from the Circle data from 2017. And these are different days, and we basically threw all the data together in one big bundle that co-registered them. And now in smaller regions where there really is no correlation visually, you can actually see very precise change detection. And so, you know, this little ice piece here is about the same, and this is broken off. And so that's a really, you know, it opens up a large domain of type of exploitations of the data that you couldn't otherwise do.
Thank you so much, Matt. I will suggest that there's an interesting conversation going on there, and I love the final slide. Thank you again for your presentation. Yep. And we'll look forward to talking to you more. It's time to transition now to our final speaker. Okay. So we have Damien Sileo. I hope I pronounced your name right. This is a highlighted talk. The title is Unsupervised Pre-Training of Neural Networks on Satellite Imagery Improves Food Insecurity Forecasting. Damien, I see your slide, so take it away.
Okay, thank you. Yes, I'm Damien Sileo, it's pronounced like that, and I'm going to present you a work, a joint work with my colleagues at KU Leuven in Belgium. So what we're dealing with is geotemporal tasks where you have a region of Earth and a time frame, and you want to predict something about that region and that time frame. Sorry, I'm putting my code. And you want to predict something based on features, and a popular way to do it is to use a machine learning model on a trend set. And a more concrete example of such a task is food insecurity prediction. So we want to predict the extent to which the population is in a systemic danger of due to the lack of food. And so there is a previous work doing this task based on features. So there are many relevant features that we can think of. For instance, population features, demographics, environmental factors, geopolitical information, food price, or stuff like that. And you learn a model to learn the relationship between the two. But to do so, you have to think of many factors, and it can be complicated to turn them into numerical features. And you are very much dependent on these numerical features. So another way to do it is to rely on satellite images. It makes sense because based on satellite images, you can guess or estimate many factors. You can estimate, you can see that on satellite images, the influence of economics, because developed countries have different appearances on satellite images, or you can also see the influence of weather or agricultural factors, how the agriculture is going, and so you can guess many information from the raw images, but it is complicated and you can use a model that can learn to extract all the relevant information by itself based on the raw information. And we can do that because we have good neural representation. So neural representation works by using filters that capture some patterns in the image. And then you can use filters over filters to capture patterns over patterns. And so you can capture complicated patterns on the image. And it's the purpose of using a deep neural network to compute and to use deep patterns. But to have deep patterns, you have to have a complicated network that have many parameters to estimate. And so it makes it complicated to use a neural network if you directly learn from the data. So you could directly learn what you want from the data by using directly the downstream tasks that you want, for instance, food insecurity prediction as a training, but it will not be it will not allow the network to learn useful things because it will not have enough data. So one popular way to do it is to use contrastive pre-training or pre-training in general. So with pre-training, we use pretext tasks to infuse capabilities into the feature extractors, so that then you can use the feature extractors for downstream tasks. And an example of trendy pre-training method is contrastive pre-training. So the idea is that similar images appear in similar contexts. And so you can here consider that an image is a context. And you can take some crop images from an image, for instance, two images that are cropped from the image of a cat, and they are probably similar. And you can also take images from crop images from different images, and they are dissimilar. But to be able to tell that, to tell that, you have to have a good representation. And the idea of contrastive pre-training is to use this method to generate data and to learn to distinguish images that come from similar or dissimilar contexts. And so we can use a learning algorithm to optimize the feature extractor so that they do this task correctly. And then when we are done, we can use the feature extractors for downstream tasks. There are some works that do that kind of things with satellite images. One of them is Style2Vec. So they make positive and negative pairs based on crops that are extracted from satellite images, and they optimize representation so that similar crops have similar features, and nearby crops have similar features, and distant crops have dissimilar features. But doing that doesn't take into account the temporal dimension. And the temporal dimension can be useful because sometimes you want to predict some phenomena that depend on the time. For instance, the food insecurity. It can, well, there are some regions that are more likely to be targeted, but it's also dependent on the time. And so it's also important to take into account the time. And there is another related work that take into account the time, but they take in account the time in order to ignore it, which is not what we want. So they make representations that are time invariant. And for their task, it works well to have this time invariance. But for our task, the task that we choose as an illustration, it doesn't really make sense. So the research questions are the following. First off, can pre-trained satellite imagery representation improve performance when predicting food insecurity, which is one of the downstream tasks that we choose? And secondly, how can we intelligently take into account the time when we construct pairs of similar and dissimilar examples, and how does it influence the downstream task performance? So to represent a region or where we want to do the prediction, we decompose that region into patches, and we represent the patch with the feature extractor, and then we will aggregate the patches based on all the patches of a region to make a prediction. So we do that. We could directly use a convolutional neural network on an area, but it wouldn't work well because it will not be fine-grained enough. So we do this kind of thing. And then once we have aggregated the representations over a region, an administrative region, we do the prediction with a linear model or a log linear model. And we will apply some pre-training strategies on that at that stage on the feature extraction network. And then we learn the feature, how the features relate to the downstream task. So we are going to test different ways to form some pairs of temporal and of regions based on temporal and spatial criterion. So one way to do it is the tail-to-wake way. We just ignore the time dimension, and we will evaluate that. But we will also take in account the time dimension. So instead of making pairs of similar and dissimilar, distant and close regions based on the spatial characteristic, we will work on a cube where we also take in account the time. So we work in 3 dimensions. So the data that we use for our experiment is the Landsat 8 satellite images data that was extracted since 2013. And we do some pre-processing on these images, which is that we aggregate the images with 4 months composite in order to remove the clouds that are obstructing the image too much. And so we compose the image over 4 months in order to have that that cleaner representation. And it was helpful. So, and the data that we use for food insecurity prediction, it comes from the World Bank food crisis. And so it was annotated by the organization that classifies several levels of food crisis. And we have a multi-class evaluation and also a binary evaluation where we have a cutoff. We evaluate, we remove the middle, and we perform a binary classification. And so the network that we use a ResNet 18 network, which is a smaller version than the ResNet 15. So it's a convolutional neural network. And so here are the hyperparameters that we use. We did some cross validations to find the best parameters, but I'm not going to detail that a lot. And so we evaluate the following thresholds to form positive and negative pairs. We use 4 months, 12 months, and 36 months. So using 36 months is equivalent to discarding the time totally. And we also use different spatial thresholds that are measured in angles, and we compare them. And the evaluation of using the pre-training and then doing the evaluation on the food insecurity crisis detection is the following. So here you can see in the different colors the different aggregation methods of several patches, and we can see that doing a voting on the patch that is a majority voting works the best. So we can only look at that. It's using many patches obviously helps. And we can see that the time variant method of contrastive pre-training achieves superior results. And also we find that using a moderately high, like average spatial threshold to form the pairs work the best. So it makes sense because like there has to be a sufficient distance between the patches for them to be different enough, and so it's and to have good representations. So it's one downstream task, but for other downstream tasks, we might have some different results. And we also compare here more thoroughly with the previous work that use handcrafted features. And we find that when we, just by using a pre-trained network, we can outperform the manual handcrafted features. So it's in itself quite interesting. And we also try to evaluate several pre-training methods for the neural networks. So we do random initialization, and it doesn't work well. But we also tried to do an ImageNet pre-training, and it's also not as good. And something interesting to notice is that when we combine the prediction of our neural network that is trained on satellite images and the manual features, we achieve the best results. So it's there are some things that are not captured by the satellite imageries, which was expected, but it's surprising that the satellite images work so well. And the results that we have, they hold whether we have many or few labels. So we did another experiment where we reduce artificially the number of labels that we have for the downstream task. And even when we have quite a few labels, the performance that we have doesn't decrease that much. So even, yes, with few labels, we still are able to outperform the manual encrypted features. So, so the conclusions are the following. Exploiting unlabeled satellite imagery helps for geotemporal downstream tasks, at least this one, and a pre-trained model achieves the highest performance when it uses a spatiotemporal contrastive objective. So our works have some limitations. One of them is the scale. We could scale up our models to larger models and larger data sets, but we are computationally a bit limited because it's we have there are a lot of big images, and so it's hard to scale. One limitation of the work is that we also don't predict the future, but like the trend test bit of the previous work, it was not done in the temporally ordered way, and doing it by predicting the future instead of predicting the past, sometimes it will be very interesting. And it will be also interesting to test many other downstream tasks other than the food insecurity prediction, to see the influence of satellite images as features for geotemporal tasks. So it was a bit quick. We should have more time for questions.
Great job. Super exciting work, Damien. Let's see, looking over at the Slack channel, let's see what we have. Emma says, great talk. Thank you so much. I guess let's see what time we've got here. So yeah, we just have a minute left. If I don't see a question pop up, I'll just say, what's next for you? You have a minute to say a little bit more about that if you want to.
Yeah, I think it would have been interesting to work with more downstream tasks and to have a kind of benchmark evaluation that rely on socioeconomic, or like there are many things that we could predict from image representations that come from satellite data. And I think that making a kind of benchmark where we test many other tasks like prediction of GDP, stock markets, or many other data, I think it will be interesting.
Okay, hey, one question just popped in. Also, I want to say I'm writing with my Leuven pen. I spent some time in Leuven for a workshop. Wonderful town. The question is from Manmeet Singh. Can you please explain more on the target food data? Oh, and also from Emma, if you could also tell us the best reference from your work. And if you can access Slack today, maybe you can post a link to your best reference. So those are the two final questions. Yeah, you got about it. You could probably address that in a minute if you want to share. So explain more on the target food data and share with us a favorite link to your favorite reference to your work.
So yeah, I'm not sure what I should add more. Like it's the World Book, the World Bank Food Crisis, which is an organization annotated some food crisis over the time and over some administrative regions, and they determine the extent to which there is a food crisis by using it's mentioned here an analytical framework. So I think that they have some criterion in there that they determine to map the levels to the situation. But yeah, I don't remember more interesting information about that. So I point you towards the reference here.
Okay, thank you so much. Well, we're basically at time for the session. Thank you, Damien. Slack channel, if you think of other things you want to share with us there. And I just want to say, all the speakers, if you want to put your cameras on at the last minute here, I want to say from behalf of the audience and the workshop organizers, thank you so much. And thank you, Susan, and thank you, Brian, for keeping us flowing really beautifully. Great conversations, everybody. Same Slack channel for this afternoon, and hopefully you can come to our afternoon follow-on Seamless AI sessions. And also enjoy your 15-minute break. Get some coffee or tea or whatever you like, and we'll hopefully see you at the plenary on Trustworthy AI. Thank you, everybody.